Before we begin this episode, we would like to say that in the spirit of reconciliation, that we acknowledge the traditional custodians of country throughout Australia and their connections to the land, sea and community. We pay our respects to the elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander people today. Welcome back to another episode of Spaghettification on the Astropunk.
And I'm Steffi. Today we have with us Nataliea Lowson. Nataliea is a PhD student at the University of Southern Queensland studying the atmospheres of planets around other stars. She also makes movies about astronomy and what it's like to be an astrophysicist on social media. We're really pleased that she's able to join us today. Welcome.
Hi, thank you for having me.
Thank you for being here.
I don't think we've had anyone talking about exoplanets yet, so I'm really excited about quizzing you about everything.
Well, hopefully I know all the answers, but if I don't, I'll just fall back and say I'm just a student.
The most expert on them of the three of us.
I know nothing about exoplanets, so we're all
Do you want to ask the first question then, Mark?
Maybe. I'll think about it. Exoplanets is it's a very niche part of astronomy. But prior to getting into exoplanets, what actually led you into astronomy itself?
Yeah, that's a story.
We're here to listen. Tell us the story.
Well, it goes back, 20 years ago. 2003 or 2004. 2004, so almost 20 years ago, when I was in primary school, and I was in, I don't know if you guys had this in your schools, but
No, we
did you
still
ever
had
have
stone tablets when I was at school.
Did you ever have combined classes?
Yeah, as in year levels?
Yeah, so there would be a class where it would be like your year level, but then there'd be one class where it would be half people in your year, but then half either the year above or below.
Oh yeah, like 4, 5, things like that.
Yeah.
Yeah, no, once again, stone tablets, boys in one school, girls in another school. No, I'm a child of I went to school in the 80s, and it was just everyone fend for themselves. So we didn't have, but I do know what you're talking about.
Yeah, mixed class. I was in one of those, and the non-mixed class learnt about the solar system, and the mixed class learnt about bugs, and bugs are really cool. I'm really happy I learnt about bugs, but for some reason I thought it was really important that I was like, I'm not learning about this space stuff and everybody else is. So I'm going to take it upon myself to learn. And so I borrowed books from the library and would read about it and look at the pretty pictures of all the planets in our solar system. And I was like, this looks pretty cool. I wonder what it'd be like to do this as a job, not knowing what it actually entails to become an astronomer. But I basically had that image in my mind and ever since then. And then when I was about 16, I found out that to be an astronomer, you have to do science and maths. And I was okay at it, which made me be like, oh, I don't know if I can do this. That seems pretty difficult. But I was predetermined because all this time I was like, yes, this is what I want to do. So going into, in the ACT, we call it college, year 11 and 12. Going into college, I was like, yep, going to do physics, going to do maths, going to try my best. And that's basically how I got there in the end. And here I am doing my PhD, so still chugging along, trying to become an astronomer.
Yeah, I think you're already an astronomer.
Oh, thanks.
So you are a researcher, a published researcher.
Yes.
You are a published researcher. There we go, words. And your research is on exoplanets, as we've already mentioned. So before we go into the nitty-gritty, how are we actually able to find planets around other stars?
That's a really good question. It depends on what you're looking for, but there are a few different techniques where the easiest one, and also the one that's most common, is known as a transiting technique. And what I like to use as a comparison is if you're seeing a solar eclipse, so when the moon goes in front of the sun, and if it's a total solar eclipse, you get to see this, which is coming from the sun, and that's essentially the sun's atmosphere or upper layer of the atmosphere. And it's a similar thing with planets, except the planet is way smaller than the star that it's orbiting, so it's not going to block out the complete star, but it will block out some of the light. And so the way you can detect this is if you have a telescope pointing at a certain star, and over a certain period of time, you see these dips occurring in the light periodically, as in they're repeating the same time over and over again, you can infer that there's a planet there. But sometimes in the past, especially when, the exoplanet field just was starting out, a lot of these tended to be what we call false positives, which essentially is rather than it being a star, than a planet, it was actually another star, which is sad. But as we've gotten better at these techniques, we know how to rule out if that's the case. So that's the most common way. But there are a few other ways. Like there is another way called direct imaging, which is looking at the star, and then you use an object known as a coronagraph, where it blocks out the light coming from the host star. And if you have planets quite far out and they are also really young and giving off some heat left over from their formation, you can actually detect them in this technique. And so that's what I mean when I say it depends on what you're looking for, because with direct imaging, you get to see planets that are really far out and also really young. And with transiting, you can't necessarily do that. The planets have to be quite close to the star in order for you to see this dip in the light very periodically, because otherwise we'd be waiting years if you want to see a planet very far out. Because I think Saturn, I was looking up yesterday, Saturn takes like 9 years in order for it to do one orbit around the sun. So yes, depends on what you're looking for.
Yeah, so are you looking for more of the larger planets or more of the Earth-sized sort of planets?
I mean, I think everybody at this stage really wants to find like second Earth, like that. At least I know that's what the public is very interested in.
Yes, yeah,
Absolutely. That's all we care about.
Yeah,
We don't
screw
care
finding
about
other
how
planets
much.
and what they look like and if they're different to our solar system. Where's the twin? Where's the Earth twin?
Where's the other humans? It's on the other side of the sun, isn't it? The other planet.
Yeah, Planet X.
Anyone remember that there was a movie where we sent someone to a planet on the other side of the sun, and they sent someone to our planet from their side of the sun.
I think so.
And so they landed, and they thought they'd landed on their own planet, even though they were on the other planet. It's a very old movie. Very old movie.
How old are we talking?
Oh man, probably 50s or 60s.
Sort of like that. But
everyone wants that.
Everyone does want that.
That's what the public want. Where's the next planet with life on it?
I mean, let's be honest. If someone does find that, that will be a Nobel Prize for them. But so far, we have not successfully found planets with other life. But that's not to say that we potentially can't. There are ways.
So with what you do, you're obviously using high-powered equipment. Is this the sort of thing that amateur astronomers can do from their backyard or from a dark sky site with their own equipment?
It would depend.
Conflict of interest.
So the way that the easiest way that I can think about the public getting involved in a planet detection is I'm pretty sure there are programs, if not there was programs, where they would get people from the public to look at light curves that were observed with space telescopes.
Yeah, I think I've seen
basically,
that. Is that like Zooniverse or?
Yeah, like Zooniverse, but instead of galaxies, it would be for planet transits.
Yep.
And if you manage to find something, you could then be on a paper of a planet discovery. But it's really hard because we're looking at stars quite far away, and the dip. One good analogy that I've heard is even if you're looking at like, I think a Jupiter-sized planet close into their host star, it's equivalent to looking for a firefly in front of a high beam car. So like, it's not really something you can do with just a standard telescope that amateur astronomers can buy. It does take a little bit more.
Yeah.
But also because of the surveys that we have, they're just finding them at such fast rates that it'd be hard to keep up.
Yeah. But you mentioned that binary stars often mimic, or maybe the other way around, but binary stars have a similar sort of signal to planets in transit, so that might be a little bit brighter, might be a bit easier to monitor for amateurs.
It gives off a different shape.
Yeah.
Ultimately. Yeah, because it's a bigger bigger radius, a bigger size against the host star size. And
So your most recent work is on looking at atmospheres of these planets. How do we see the atmospheres, and what can it tell us?
there's two ways you can see atmospheres. There is what's called a primary transit, which is what I was talking about before, when the planet is going in front of the star. And the part of the atmosphere that you're seeing when this happens is called the day-night terminator. And that's essentially the sunrise-sunset region of the atmosphere. And that's coming back to that image of when you have a words escaping me, but basically an eclipse of the moon in front of the sun. When you're getting that area of the planet.
Yeah.
And we can subtract the starlight from these observations, which gives us the atmosphere. The second way that you can look at an atmosphere is called a secondary transit. And that is when a planet is just about to go behind the host star. So it's on the other side of the star. And what's happening here is light is actually projecting off of the host star onto the day side of the planet. So you'd be getting to see the day side of the planet atmosphere. So that's the two types of ways you can do it. But also you can do it as it's orbiting around. But those are the most two common ways because it creates a very specific shape that we are able to identify quite easily.
What can it tell us? You missed a bit. I want to
What
know
did it tell
what
us?
like.
My
what can it tell
apologies.
us? So you've got your data. What can that tell us about those planets? Like, what information do we get?
Well, we can know what molecules are in the planet. That will depend on what region of light we observe in. So you might have seen in press releases to do with JWST that there's a lot of buzz to do with planets, and that's because infrared light is essentially the perfect region for if you're wanting to look at molecules like water and methane, oxygen 3, and that's due to if we try and do this on the ground with ground-based telescopes, a lot of the infrared light in these key regions gets scattered from our own atmosphere. Damn us. I mean, we kind of need it to breathe, but it's also getting in the way of my research. And yeah, there are other areas of lights that will tell you different things. Like if you look in UV, you can see atmosphere escape, which is pretty cool. So you can tell if an atmosphere is actually evaporating off the planet. If you're looking in optical, you get to see other types of molecules, which tend to be more prominent in the optical region. But aside from molecular detections, other things that you can see on these planets are if they have clouds on it, if they have haze, which is kind of similar to fog. If there's wind, you can calculate wind speeds on planets. Yeah, I know, right? They're cool. You can calculate if the planet's rotation, so like how often it rotates on its axis. So on Earth, it rotates once every 24 hours. That's a day for us. What else? There's other things too, but those are the things I can think off the top of my head. So there's a lot.
Yeah,
there's a lot of different things.
So I have a question. So since we've just mentioned that planets can take a while to orbit their star, or they can take a really short time to orbit their star, do you have to be really lucky when you're trying to get these images or observations of the planet's atmosphere? If you're looking at these particular orientations of, the planet and the star and the telescope, is it tricky to do, or is it because they're so far away, it all sort of averages out?
It definitely is tricky. Luckily, there's a lot of software that's been developed by the community, which helps you be able to analyze it and also subtract away the host star. But I can't remember the first part of the question. Can you please repeat it?
Yeah, it was like if you want a particular transit, do you have to time it down to like a really precise sort of measurement?
Yeah, you do. And that comes into what I was first talking about, where you can, if you're seeing this happen many times over, you can determine it's a planet orbiting around a star. What that means is you can also predict when it's going to be in a certain spot.
Yeah.
So when you're applying to observe on really big ground-based telescopes or space-based telescopes like Hubble and JWST, you can essentially, what you have to do is you have to simulate when you're what you would see, what you think you would see, and you'd have to do the calculations of when exactly is this transit going to occur. Otherwise, you're not going to get time. It's like a very basic step that they expect you to do.
Yeah, of course.
In order to get to observe. But it's really cool. Like, for example, I won't talk too much about it because it hasn't been published yet, but my second paper is actually...
Heard it here first on Spaghettification podcast. Breaking news.
My second paper is a planet discovery paper.
Mm-hmm.
And yeah, it's very exciting. Very exciting to be part of that. And a part of that process actually involved me applying to do follow-up observations on a space telescope called Chaos.
Oh, cool.
And this telescope basically looked at the light, the dip. And we were able to actually calculate that these two planets would be transiting its host star in about a 17-hour period. So if we observe that star for 17 hours, we would see one planet transiting, and then we'd see the next planet transiting. And our simulation for the proposal that we submitted versus the data we actually got, it was basically spot on, which is really cool to see that in person, where you're seeing these two dips occurring basically where you calculated that they would occur.
So I'm going to go back a step. So you're saying you calculated where it was going to be. How did you know that the star you were going to look at was going to have one of these planets flying around it? Like, what's the step before that? Obviously,
yeah.
That's what it's going to look like.
How do you do a planet? How do you calculate a planet discovery?
Yeah, how do you know that the star you want to look at is going to have a planet around it?
Yeah,
like,
so
how do you work that out?
We actually picked up the planet detection in tests, but the test data we needed to do follow-up to confirm it, because these are quite small planets. So we can't just do follow-up with ground-based telescopes or wait for another test sector to go around, which is how we were able to calculate when it would be with this particular telescope, because we had already identified it in some test data. So
and Tess is the follow-up to Kepler, right?
Yes. So that's me doing science jargon while forgetting that I shouldn't be doing science jargon. So TESS stands for the Transiting Exoplanet Survey Satellite, and its main goal is to find exoplanets around nearby bright stars. And so that's like main sequence, like G, K stars and above. So Kepler was great. It found a lot of planets. The downfall of Kepler was that not long after it launched, one of its gyroscopes broke, which was in charge of being able to maneuver the telescope to move around the sky. And what this meant was that the telescope was actually fixated on one spot of the sky and couldn't move off that spot. So astronomers had to quickly come up with a new survey for that small patch of sky. So it found a lot of planets in a very specific part of the sky, very deep into the sky, whereas TESS is actually covering the entire sky. But not as deep as Kepler went.
And I guess so, because I'm a extragalactic astronomer, when I think of going deep, I'm looking at things that are far away and also far back in time. But because you're working on stars and things inside the Milky Way, you're looking for things that are brighter is probably more useful, right? Because if it's a brighter star, you can get a better signal. I'm guessing.
Well, it depends. It depends. Like, yes, it's good. But if you're looking for a small planet, it can be not so great. So, for example, if you're wanting to find an Earth-like planet around the sun, it's blocking out a lot less light than if you were to look at a Jupiter planet orbiting the sun. So if you're looking for more rocky planets, we tend to actually observe them around M dwarfs because they are smaller, which means that the ratio between the planet size and the star size is not as large, which is, for example, you might have heard of the TRAPPIST system.
Yep.
Which there's, oh gosh,
6 or
I
7
think,
or
yeah,
something.
6 or 7. So B, C, D, E, F. I think goes up to G. I'll look this up. But yes, there's a lot of planets. They're all
Almost
with
alphabet long.
almost alphabet long. They are within the orbit of Mercury equivalent,
Mhm.
and they are all like Earth-sized planets, essentially. They're all rocky planets.
Awesome.
So what do we got? We got 1, 2, 3, 4, 5, 6, 7.
7. Yep. Yeah. Yeah, because like so when I was a kid in the 90s, we got like 3 decades here. So so the first exoplanets were discovered in 1990, I think.
92. However,
92,
that's
there we go.
disputed. That is
Disputed, yeah.
disputed. Some people will say 95. Other
Yeah.
people will say 92.
Well, anyway, a very early in the exoplanet sort of field.
Yes.
And so when I was looking at books that would talk about things like the Drake equation, which has a lot of different things that we'd like to measure about the universe, but at the time it was very difficult to measure any of them, like how many stars have planets, how many planets are around each star. And so it was sort of like, we know that the solar system has, at that time 9 planets, but we would say 8 planets now, because Pluto isn't a planet. But
Yes, it is.
no, it's not.
Ongoing debate.
I'm just trying to start travel.
So yeah, it was really a debate about whether stars did have planets, if there was something special about our solar system, or if there were just planets out there that we couldn't see. And I guess these days you probably can correct me, but it seems like we find that actually most stars do have planets. They're pretty ubiquitous, and then I guess it's finding how many planets there are in a solar system is something that we can start to do now as we get better and better data and can look at like tinier and tinier dips. So yeah, I think the TRAPPIST one was sort of one of the first ones where it was like, oh, there can be systems with lots of planets around them. Like I remember in 2016 when it was announced, I was in the Netherlands at Leiden, and it was just like a real like, ooh, hey, like this is actually like it was sort of whispers before the actual announcement, but it was just like, because usually it'd been like 1 or 2 or maybe 3 planets, but yeah.
TRAPPIST was particularly special because of the size, like finding so many Earth-sized planets just within the habitable zone. It was the fact that they were Earth-sized, and also there were planets in the habitable zone, which is like a big deal at the time.
Yeah.
Which for those who don't know what the habitable zone is, that's essentially a region.
It's the Goldilocks zone.
It's a region in a planetary system where the planet is far enough from the star that there should be liquid water, in theory, on the surface of the planet. Not too hot, not too cold.
Yeah.
Just right.
Just right.
Yeah.
Kellogg's. We'll call it the Kellogg's zone.
I mean, it's crazy how within 30 years, just the mindset has completely changed. Like there's over 5,000 planets that have now been confirmed as being actual planets,
and
which
probably
is crazy.
Twice that of candidate planets that just need to be followed up, or
yeah, no, there's a few
don't even
more
know.
candidate planets.
Yeah.
I think the candidate planets are above 10,000.
Yeah.
I remember hearing a number a couple of days ago, and I think it was around that. But like, 5,000 still, that's a lot.
That's a lot.
And yeah, I find it really cool now that in school, in high schools, kids will be learning that, planets are just another thing.
Yeah,
it's
exciting.
common.
Yeah.
Not something we learnt about when we were at school.
No. Well, sort of leading into that sort of, I guess, future of discovery, you're also working on a new space telescope called Twinkle, and you're working on sort of developing the science program, or how to get the most science out of it. Can you tell us a bit more about that? Because I was really excited when I first heard about this.
And is Twinkle an acronym, or does it just relate to Twinkle Twinkle Little Star?
I get this question a lot. I have tried to find out the origin of the name, and I have not been successful. So I do not know why it's called Twinkle. I love that it's called Twinkle.
Yeah.
Cool name.
But no, it is not an acronym. I can confirm that.
Damn it.
Yeah. So Twinkle is the first privately funded space telescope for the science community. My university, the University of Southern Queensland, is the only Australian institution which is a founding member of the mission, which essentially means that we are helping create what this survey is actually going to include.
Yeah.
And we're also a part of, I guess, the journey from the stages of planning to lift off and beyond. It's going to, estimated launch is next year. It has been delayed, but that's pretty normal for any telescope that goes into orbit.
Look, is it really astronomy if the project's not delayed?
I know, right? I know. But the main aims of the mission is it's actually going to be broken down into 2 surveys. There's going to be a solar system component and an extrasolar component, where in the solar system component, it'll give members of the survey the opportunity to be able to research objects within our solar system, whether that be asteroids, comets, or the outer planets, because the way that the telescope will be configured is it'll always be facing to the outer planets, so we won't be able to look at Venus and Mercury. Sad.
Okay.
And yes, very sad face. And the other side of the survey is going to be looking at exoplanets and potentially also the spectroscopy of stars and brown dwarfs.
Oh,
and
there's my favorite word. Spectroscopy.
Which ones?
Spectroscopy.
It
love it.
finally happened. And I think from early days of being on the team, what seems to be the side that a lot of the members are excited about is the exoplanet aspect, because the light that Twinkle will be observing in is going to include infrared. So it's a bit of optical and infrared. Specifically, it's going to be about 0.5 to 4.5 micrometers.
Okay,
The green to mid-infrared. That is perfect atmosphere characterization region, as I mentioned before. So a lot of people, including myself, are very excited to use the mission to do atmosphere characterization.
Yeah.
And my involvement at the moment, as you said, is helping with preparing the mission. And so that's including using our Mount Kent telescopes, which is about a 20-minute drive outside of USQ in Toowoomba. And we're going to be essentially doing observations on the objects that we intend to observe with Twinkle and refining the parameters, because sometimes there are specific parameters with planets where if you don't observe them frequently enough, they will decay. And so if you then try to observe a planet, it'll be out of time with when you predict.
Wow.
So you have to, so you have to constantly re-observe them so that you know exactly when it's going to transit.
Because I'm guessing, that's over the course of, like, say, years or something. It's so the planet is sort of spiraling in towards the sun, I'm guessing, or moving away from the sun, or
it would be a bunch of different factors.
Especially
if it's a planet that is in a multi-planet system, like the gravitational pull of the other planets in the system will interact with it. We need to constantly look at these and make sure that's up to date, and that's part of what I will be doing with helping prepare from the ground for the mission, because essentially with these space missions where there's like a planned goal, you want to try and make sure you have everything planned as possible as you can before it launches, so that you have it up in orbit, because once it's up in orbit, you want to be able to get as much science done and not essentially waste time having to calibrate things and make sure that everything's working properly. So
so the scope that you're going to out in Toowoomba, that's the one you're going to be using to do your test data with. Is that what you're saying? Yeah. So what is that telescope? What sort of scope is it?
So they are 0.7 meter telescopes, and they are plane wave CDK 700 telescopes, if that means anything to
absolutely
the
does,
people who are into the techie side of telescopes.
So
And
we
it's,
have,
it's
we have a
part of
lot of listeners who are astrophotographers, so they'll
Amazing.
absolutely be drooling over the fact that you're using plane waves.
Nice. Yeah. So it's part of the configuration called Minerva Australis, and we are the southern component of an observatory, where the northern part, I believe, is in the US. And the telescopes themselves, they do a photometry in the GRIZ bands. And it also has a high resolution spectrograph, as you like the term spectrograph.
I just like spectroscopy. It's such a cool
Attached
thing.
to it.
It doesn't get enough limelight.
Yeah, so these telescopes can be used for spectroscopic or photometric observations. I have personally only used them for photometric observations, especially predominantly to do with twinkle. And yeah, they're very cool. I like observing on them. They do a lot of follow-up observations for tests as well. And if you're wanting to know about the resolution of the spectrograph, it's
I'll throw it in there.
80,000.
Wow, that's
Which is definitely in the high resolution.
yeah. I work on
Absolutely.
galaxies, so like 20 is good.
Yeah. So when it comes to planets,
Yeah.
we define high resolution as anything above, approximately above 25,000.
Where do you think the future of exoplanet study will take us?
That's a great question. And is it completely biased if I say atmosphere characterization?
No, no, not at all. You can say whatever you want to say. You can give multiple answers. You can say that it's atmospheric, whatever it was you said, or it could be something else. Like, where do you personally think you? All right, so we'll do what I did last time, Steph. We'll break it into two. Where do you want it to go,
Yeah.
and where do you think it's going to go?
Well, I want it to go to atmosphere characterization, but I also think it's going to go to atmosphere characterization. And the reason I say that is because we've spent the last 30 years-ish finding these planets, figuring out their orbital parameters, characteristics like how big they are, how much they weigh, but we don't know a lot about the chemical components in terms of what they're made of. And that's where these next generation telescopes are coming in. So JWST is exciting, as I've said, because it can look in the infrared, which is perfect for atmosphere follow-up. And so we have already, within the less than a year of time on JWST, have learned quite a bit about some of the planets where there were multiple observations using ground-based telescopes and Hubble. And we thought we knew them. And then JWST was like, nope. Turns out you don't. They're actually completely different. So
You know nothing.
So it's already changing the field in the short period of time that it's been around. There's also Twinkle, of course, as I mentioned, which will help assist to this. And I didn't say before, but with something as great spec-wise as JWST, Twinkle is not as impressive spec-wise. It's much smaller. Aperture-wise, it's also covering less of the wavelength band as JWST, but it makes up in the fact that it's a dedicated survey. So for all of the time on the Webb telescope that people will be applying for, it's already, I think the stat that came out was that in the last submission for observing on JWST, it was 20% oversubscribed, which is more than Hubble ever was. Which is insane. This is the first
new toy.
Yeah. Everyone wants time on it, but that means that there will be awesome science which doesn't get time on it, because ultimately the TAC, which is the committee of people that decide who gets time, they have to choose the best of the best, and what is that essentially comes down to the best with Webb. Not necessarily that it's not interesting science. And so having dedicated missions like Twinkle is important, because then they can take some of those science questions, which could still be answered with Twinkle, just not as high res, but you still get answers. And then there's also Ariel, which is coming out in 2029, fingers crossed, which is purely atmosphere characterization. Like the goal of that survey is to look at 1,000 exoplanet atmospheres. So these are planets that we already know of. It's not going to be a discovery survey like TESS.
Yeah.
But it's just going to basically like hone in on in more detail on like what's going on with these planets, whether that means characterizing it because it wasn't characterized with JWST, or whether it's just characterizing in more detail, like understanding weather in more detail on these planets, potentially. So yeah, it's insane. Like this really is the time for atmospheres in terms of planets.
Yeah.
And I'm excited for it. I'm very excited for it.
I had a sort of technical question. One of the reasons that I sort of think of the infrared as a good place to look for planets is because of something called black body radiation, which is sort of the light that the planet gets from the star that gets absorbed by the planet and then radiated back out at a different wavelength, which depending on the size and all that tends to be in the infrared. But how much of the infrared light that you're seeing from planets is the light from the planet itself, and how much is still sort of reflected light from the star? Is it? I'm guessing the light is still mostly from the star that you have to sort of subtract off.
I mean, again, it's firefly and headlights. From that raw data, you do not see the planet. You have to subtract the stellar component if you're going to get any chance of seeing the atmosphere of the planet. But yes, as I've said, the techniques that we've come up with in the last few decades, we've really refined it. So we're pretty confident in the way that it works, because this has been repeated many, many times with different planets, and we've been able to detect something. So
and so my other question is, so one cool thing about Kepler so when I did my master's, when Kepler was sort of going, was that because you're looking at these stars, and I guess with Kepler you were sort of stuck looking at the same stars, you're just looking at them with such a high cadence, or this like looking at the same star over and over again, a few days or how long later, but you could get a bunch of information about the stars themselves that we maybe hadn't seen before, because it's just a new technique of looking at them. And you could see things like supernovae, and I'm not sure if you worked on this as well, but I know at ANU they were doing a lot of this work, looking at supernovae like in their very early stages, just as the star is starting to explode, and seeing things that you couldn't see before. So like, all data has sort of the main thing that we're looking for, but then also we try and get as much juice out of it as we can. So do you see these surveys that are coming in the future with JWST or these other ones? Do you see other science coming out of those as well?
Yeah, well, back to your smaller question. Yes, I did. I did, surprisingly. Actually, I did work on some supernova research. When I was at ANU. But I mean, I talk so much about planets and how it's important for us to understand them, but without knowing information about the host star, there is information you can't understand about the planet, like especially to do with formation. So another thing I didn't mention before, in terms of what you were asking me, like what can you find out from planets, you can actually figure out how they formed looking at their atmospheres, which is super cool. And understanding the host star of the system gives you better insight on being able to not only have a better understanding of how these planets might have formed, but also the physical parameters, because a lot of the equations that we use for like understanding radius or mass or other components do involve the host star. So if you have incorrect information about the host star, then you're going to get incorrect information about the planet as well. So they are intertwined. As much as exoplanet people are like, get that star out of my data, I don't care about it. In theory, we actually do. We just like the planet side of it more.
So I have a big question now, sort of going into a different sort of topic. You started your PhD during COVID. And what's it been like being a grad student with COVID and lockdowns and all that sort of thing?
Well, the beginning, it sucked.
Yeah.
In all honesty, because I moved up to Queensland in February of 2020.
Yeah.
And was like looking for a place to live, getting sorted into uni at USQ and whatnot. And then I immediately had to come back to Canberra
Yeah.
because they started closing the borders, and I didn't have a place to live at that stage.
Oh no.
So I essentially came back and was doing the first few months of my PhD remotely in Canberra.
Yeah.
And remotely, I was able to find a place. And then I was able to come up here temporarily when the border was open for like 2 weeks. Somehow I look back on it and I'm like, I don't know how organized for like furniture to be moved up as well as myself, but it happened.
Yeah.
So from that side of things, it was annoying and difficult. But once I was up here, because they were so strict about it, you're like, cool, I'm super safe. It has been a struggle. There were definitely, at the beginning of my PhD, things that I was having trouble with in terms of code, that if I was just in the room with my supervisor, it would have been solved like almost instantaneously. But because I was at distance, it got dragged on just because it's hard to describe problems if you can't see them. And so that was one side of it, but also the travel. It turns out, well, I already knew this, but for people who are listening, who don't do academic research, travel is a key part of the job. And that's purely because you might want to collaborate with people and it's easier to do things face to face. But also if you're trying to establish a name for yourself, you want to go to conferences, you want to get your name out there, you want to talk to people. You can do it online and it can be really well done if it's done correctly. But not a lot of people have got that right so far. It's still very much in the testing phase. And COVID did help, I think, to move things along faster. In terms of hybrid conferences and making it more accessible for people who are remotely attending. But in the end, being there in person is still a lot easier. And yeah, so a lot of conferences got cancelled and just not being able to meet people, like especially the Twinkle team. The project is based in London at a company called Blue Sky Space Limited. And I only met a few of them, a handful of them last year after I was able to go on my first international conference of my PhD. Yeah, the first 2 years, 2020 and 2021, it was essentially sitting around and attending things remotely and trying your best to get things done with the people that you have around you, which works sometimes, but not all the time. It was hard. I mean, I'm glad that things are starting to open up again, and like it was crazy last year. Just April onwards was just travel. It was definitely a challenge, and I really felt for the students that were finishing. I mean,
Definitely.
I was, in a sense, grateful that I was just at the beginning, and I still had a few years ahead of me as a buffer while the world was trying to figure this thing out. But for the students who were finishing up and trying to find jobs, I can't imagine how difficult it must have been to get through that.
Yeah, it's one of those, like, I basically didn't do any research at all for 2021 because like here in Melbourne we were locked down for a good part of it, and but teaching online, even that was just like, oh, this sucks. Like trying to help my students out with problems on the computers, it's impossible. It's like,
I became a primary school teacher and a high school teacher during lockdown. That was a lot of fun.
I think a lot of parents gained more respect for teachers through lockdown.
I already had respect for teachers, I absolutely did. But I ended up trying to run a business and teach and make sure 2 kids were doing their school. And I didn't come out of the other side very well, but that's okay. These things happen.
Yeah,
but it's a learning lesson for everyone.
Absolutely, wasn't it? It was a massive learning lesson, that's for sure. So I couldn't imagine trying to do uni like that through lockdown.
I mean, I'm currently in the extension phase of my PhD, which is pretty common for people to go over the 2.5 or 3 year time period that they thought they would be in for Australians. And I don't know, sometimes I feel guilty that I'm behind, but then I'm like, actually, there was that whole year where
life was pretty shit for a big period of time.
There was that whole year where things just were completely not the way they were supposed to be, and I wasn't allowed to travel, so it's okay. Cut yourself some slack.
Go easy on yourself. Now, when you're not discovering exoplanets, What do you do for hobbies? What do you do for fun?
I like going on walks. Oh my gosh, breaks. It's good at the
Dating
end of the
profile.
day
I
to
like going
just
on boardwalk.
yeah. I like going for long walks on the beach. No, I really do like going outdoors. It's fun. And I also like doing cross stitch. And I actually taught myself how to do crochet last year because a family member was having a kid, and I was like, this is a good excuse for me to learn how to do some amigurumi. So I'm actually working on one right now for a friend who graduated last year with their PhD.
Yep.
And so this is like a graduation gift for them, which is very, very overdue, but they understand. They've been through the process that I've done. They're all space themed. That's the main reason. It's just to make more space stuff. You can't escape it. But like, I mean, I can show you one I'm working on right now.
Yeah, sure.
Cross stitch wise.
Oh, yeah.
Cross stitch wise. So I'm actually making this for my sister.
Oh.
It's the biggest cross stitch I've ever done before. It's gonna take up the whole thing, but it's essentially gonna be like a haunted house with a bunch of monsters and stuff
so cool.
in it. Yeah, so it's gonna have like ghosts. It's gonna have a witch and Frankenstein and stuff like that. So yeah, that's really fun, but it's gonna take forever.
I think we're into pop quiz.
The next part of our show is the spot quiz, which I didn't tell you about that, so I'm sorry. But so because we spent our whole time talking about astronomy and showing off how awesome you are at astronomy, we do like to have a bit of a quiz about something unrelated to show that, you know, scientists are the same as everyone else. We just know a lot about a very certain small part of the universe. So
to show that scientists aren't robots.
Yeah.
We aren't ChatGPT.
Maybe we should. So I have chosen nightshades for you because we choose a topic that starts with the same letter as your name. And it was really hard to find something starting with N. Like one of those things where you start thinking about it, you're just like, I cannot think of anything.
I like my idea. I like napkins. Nobody knows anything about napkins.
Well, considering I know what napkins are, but I'm struggling to figure out what a nightshade is, unless you're talking about
the plant. Yes.
Okay. Okay.
So Mac, do you want to ask the first question?
No.
No?
Yes.
Do you want me to
Let's
ask?
see how I
No. All right. How many species of nightshades are there? Here's some elevator music. Do, 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 do.
Less than 50.
I'm going thumbs down. Sorry.
More than 50.
More than
Around
50?
2,700. And the family contained 98 genera. Did I say that right? Probably not. That's okay.
I'm not a biologist.
Neither am I. One of my astronomy buddies is a biologist. I'll ask him when I see him next if that's how you say it.
Maybe that is genomes? Genera?
I think
Genera?
it's like
Yeah, it could be
the next
genera.
step up from species. Yeah.
2,000.
98 genera with 2,000 species underneath.
Yeah, loads of them.
That's a lot.
Indeed. That is a lot.
So next question is, many nightshades contain poison that derives from which group of chemicals?
Ooh.
I'm thinking very generic groups here. Like
Cyanide? It's like similar to cyanide?
Sort of similar, yeah.
But that's my final answer because I
Your
can't
final
think
answer?
any
Okay.
other than that. Yeah.
Let me do some very quick Googling to see if that counts. But the answer we're looking for is alkaloids. So not all alkaloids are harmful, but many are. Nicotine and capsaicin are two of these chemicals, and they're obviously not deadly in small doses, but in large doses they are very uncomfortable.
Well, I heard once that I don't know if I should say this.
Yeah, go on. It's all right. If it's bad, I'll edit it out. If it's not, I'll leave it in.
Well, I heard once that like apple seeds have cyanide.
Yeah.
And I think if you consume, it's like as little as 2 or 3, like that can be lethal. I don't know. Like if you actually like consume the inside of it, not if you just swallow a seed and
if you like crushed it up or something.
Yeah, something like that. I remember reading and being like, that's a really small amount for
Oh, there you go.
something that people eat very often.
Yeah.
I'm a really good Googleizer. And apple seeds can indeed be poisonous, but it takes quite a few of them to kill you.
Okay, so it's
and
more than
only if they have been crushed. So
Like
they're composed of a cyanogenic glycoside composed of cyanide and sugar.
I knew something. Even though it wasn't really.
we'll give you a
It
bonus.
was
We're
not
not,
nice.
we're not just an astronomy podcast.
I do like trivia. That is so something I do in my
Yes.
spare time. So this is the trivia side of me coming out.
Yes. That is the thing, is most astronomers do like trivia. Like, I've been kicked out of a trivia team because I was too much.
Really? Because like some of the trivia teams that I've been a part of, they're like, this is too pop culture. I don't like it. I was like, well,
I love pop culture.
yeah, like why are we here if you don't like pop culture? Like that's what
Clearly
this
they don't.
is.
Clearly, they don't watch all the Marvel movies over and over again in timeline order. God.
You're
Oh,
lucky
if
you know it.
only my name began with M and you chose Marvel as the theme. Like,
You call
We
me
might have,
Captain
yeah.
Marvel?
I'd like to think of myself more as a Jane Foster. Like, if I could be anything like Natalie Portman, I would die a
okay,
happy
good.
person.
All right, question 3. Which medicine is derived from deadly nightshade, belladonna?
Heard of it? I've definitely heard of it, but I
it's
do
one
not
of
know
those
the
ones
answer.
that-
Yeah, what is
Can I
it?
give a hint?
Oh,
Not that
okay.
she'll
Yeah,
know,
yeah,
because
yeah,
the only person here that would know from this hint is Steffi.
Mhm.
Because she's
I wonder
put
who
in
wrote these
here,
questions.
it's used as a poison in many Agatha Christie novels, but that's not where I heard about what this thing does. So
Okay. I have not read Agatha Christie.
neither have I. It's okay. You're not alone there.
I read all of them. Every single one.
Is
Steffi's
it
read-
cyanide?
No, not cyanide.
Um,
Steffi's read enough Agatha Christie for everybody.
No, I do not know.
That's true.
What is the answer?
The answer is atropine, used to treat a slow heart rate and other conditions. And also used as a poison in many Agatha Christie novels. Scopolamine is also derived from deadly nightshade.
Is that
And
like
also a
used
poison.
as a poison to kill someone, or is that used to like make it seem like someone's dead?
It increases the heart rate. So that does kill you. So it increases the heart rate. And then scopolamine is used to stop you from wanting to throw up, nausea. That's what it's called.
Some might say obsessed with Agatha Christie, but that's okay.
I read, so when I was finishing year 12, and I had a library card to Hoppers Crossing Library, I borrowed like 70 Agatha Christie books that summer. So I read literally like one a day.
Oh wow! Oh wow! I
That's
didn't even realize there was 70.
Yeah, like being
Jeez.
17 and nothing to do with your
Wow.
time is just like,
Oh,
yeah,
17 or
yeah,
17?
yeah.
Oh, okay.
So there are 70 books, but I was at the end of year 12, so I was 17, and
Oh, I see.
didn't have to.
I wasn't
do,
reading 70 Agatha Christie books at the end of year 12.
Yeah, I've only just started getting into books
Yeah.
because I never really read, unless it was like nonfiction, which I know sounds super boring, but I like learning things, so nonfiction I like
Yeah.
reading, but I'm just like, well, there's so much fiction and I want to appreciate it more. So yeah, I've like joined a book club and started reading more
Yay.
fiction books. Yeah.
I did.
It's fun.
Yeah, I read a lot when I was like a kid and teenager, and then when I got into like grad school, it just dropped off because to read so many papers. But the year before last, I read 10 books in 1 year, and last year I was like, I'm going to read 10 books again, or maybe even 12, and I read like 5 half books instead of finishing any of them.
I get a chapter into a book and I get bored, find something else to do. I've tried so many times to read, I just can't.
You know what? The Agatha Christie audiobooks are incredible. They're like 6 hours each, but just oh my gosh, if I could afford all of them.
I could listen to instead of Agatha Christie. I'm not being mean to Agatha Christie, but I'll listen to Star Talk instead. No.
All right, next question.
Back to the quiz.
Tomatoes are a type of nightshade. Are they a vegetable or a fruit?
They're a fruit. Even though I personally think they're a vegetable.
Yeah, you basically got it. So they are both. Botanically, they
yeah.
are a fruit, as the seeds are on the inside. But the thing is, a vegetable doesn't have any botanical definition. So there's sort of a case of science talk and common talk like crossing over. And so they're usually put into the vegetable category because they are not sweet and they taste savory. And so usually classed as vegetable by sensible people. But botanically, in the way that botanists classify things, they are a fruit. But there's also like no category of tree. So
Yeah.
yeah. So I will.
They're that weird enigma, like how spiders are an enigma of like, the insect world.
Spiders are what? That was a new one for me.
I think spiders are just not Like
they're not technically classified as an insect or something like that.
Isn't it because they got 8 legs or something?
I can't remember
the
the
body
exact
is
reason,
different.
but yeah, there's stuff about spiders that make them debatable, and so tomatoes are the fruit veggie version of.
I was going to say the edible
spiders belong
version.
insects belong to the class Insecta, and spiders belong to the class Arachnida, so they're not insects and they prey on insects. Technicalities.
I know, right?
All right, last question. And I think this will get an equal first, not including Fred Watson's cheat point.
Surely not. Surely.
Well, Emma did really well last week as well, so I think Emma's on joint first
4,
with
wasn't she? She on
Sarah.
4 and Sarah's on 4 as well? Or they on 4.5? Yeah, they're on 4. So you could be on 4 with Sarah Webb and Emma as well.
I didn't even know I made that many points.
Mark also can't count. It's only 2 so far.
No. Oh, is it? Oh no, it's 2. I thought it was 3.
Where's the other ones?
I see question 1 and I'm looking at the 1.
I'll pretend that I did really well.
Well, if you answer this right and get yourself a bonus point, then you will be equal.
Yeah.
So yeah. All right. Which nightshade is paprika made from?
Yeah, we're not getting any higher up that list at this point. The delicious kind.
Well, they are actually delicious. Yeah, bell peppers. The name for both the pepper
seriously?
and the spice is the same in many languages. Bell peppers make paprika.
So-
paprika.
Capsicum? Is
exactly.
that technically the term then?
Yes.
Yeah, because
And I think-
everyone says that we're weird because we call capsicums, and everyone else calls them bell peppers.
Well,
At
if
least
you
we
were
don't call.
Hungarian, you would call them pufferfish.
What's the word? What's the American word for coriander again? It's some
Cilantro.
weird name. Cilantro. Like that's just weird.
Well,
it's
I
coriander.
have given you 2 points for that, so that is pretty good because you beat me and Mark when we did it. So
Okay, cool.
I got a whopping 0.
You got 0 because I asked him about Metashiro.
Ask me what my topic was.
Mark, was it Marvel?
No, it was Metashiro.
That would have been really nice to
Metashiro,
him if
of
it had been
course.
Marvel, but I wouldn't been able to actually write any
If
questions.
it was
for
Marvel, I would have got 5 out of 5 and then some.
Oh dear.
She could have given you really obscure questions.
I've watched them far too many times.
But where's the bonus question?
The bonus
No,
point
that
was
was
the
if you
bonus
had
point.
given yourself a bonus point because you got a bonus point in question 2.
I gave you a bonus
Okay.
point for the cyanide digression because it was
Okay.
interesting.
I'll take it.
And but yeah, thank you so much, Nat, for joining us. This was
That's okay.
so interesting. Definitely an area of science that I've never gotten super into, apart from just teaching transit photometry every year for half of my life. But so many amazing things that I think we'll be able to do in the future in this field. Hopefully in a few years we can get you back and you can tell us all about some of these amazing space telescope discoveries.
Yes. Well, thank you so much for having me. I had a lot of fun and would love to come back anytime if you want to talk planets.
Well, once you win your Nobel Peace Prize for or your Nobel Prize, for that planetary discovery, we'll get you back on.
Mhm. We shall see. We shall see.
Yeah.
I thank you for having high hopes for me.
Well, we got it. But yes, thank you for joining us. It's been wonderful.
Likewise.
Thanks for listening and supporting us as we continue to learn on our podcast journey. If you would like to contribute to the podcast, you can head to www.patreon.com/Spaghettification podcast and support us for as little as 1 can of beer a day. Shout out to Steve from Homeland ZZ, Jess Stout, Paul Milvain and Andy Ladder for their ongoing support.